Good morning, student. Today is third lecture of atomic and molecular structure. Today we will discuss about VACPR theory in detail. To understand VACPR theory properly, you should know about the lone pair electrons, bond pair electrons, central atom, and some minimum requirement which is necessary to explain the structure of any molecule. So here first lone pair electrons. So lone pair electrons are those electron pairs which are not used in the bond formation. Clear? So these lone pairs are although present in the valence shell, but these electron pairs are not used in the formation of any covalent bond, and also these lone pairs are known as the unshared pair or non-bonding pair of electrons. Next is bond pairs. Bond pairs are those electron pairs which are used in the formation of covalent bond. In bond pairs, obviously we are talking that these are the pairs, electron pairs. That means two electrons are there in one pair. So in bond pair, both electron belongs to different atoms. Like if two electrons are forming a bond pair, then one electron is from one atom and other electron is from the other atom. Whereas in case of lone pair, both electron belongs to the same atom, that is central atom. In case of bond pairs, both electron belongs to the different atoms. One electron belong to the central atom and other belong to the surrounding atom. Clear? Here it will be more clear with this example, like the red dots are electrons of nitrogen and the black dots are electron of hydrogen. So here these combinations of black and red dots are known as the bond pairs because these are involved in the formation of a covalent bond between the hydrogen and nitrogen. Whereas these two red dots are lone pairs because these two are present in the valence shell of nitrogen, but these two electrons are not utilized in formation of bonds, or these are unshared. So this pair is known as the lone pair. Here nitrogen is central atom and hydrogen is surrounding atom. Clear? So here one thing is very clear, that the less electronegative atom forms the central atom, because if there are lots of atoms, it is very confusing that which one is central and which one is surrounding. So in any case, the atom which is less electronegative is taken as a central atom. Only exception is with hydrogen. Hydrogen is mostly act as surrounding atom, because also in case of the periodic properties, when we learn about the periodic properties, the place of hydrogen is quite confusing. It is having one electron in outermost shell. It is with alkali metals, but it is not able to form the ionic bond. It forms covalent bond by sharing it one electron, just like the halogens. So hydrogen is never taken as central atom, and for central atom it is a thumb rule that the atom which is having less electronegativity is taken as a central atom. Then minimum two bond pairs are required for the formation of a shape. Here we will start with the two electron pairs. In case of two electron pairs, in this case there is one central atom which is shown by this blue circle and two surrounding atoms which surrounds the central atom. As two surrounding atoms are there, that means two covalent bonds are formed between the electrons of surrounding atom and the central atom. and this gives a linear shape to the molecule. Here some examples are given. Examples of the linear molecule is BeH2, CO2, HCN. Here in first example you can see that Be is having 2 electrons in an outermost shell, and these 2 electrons form covalent bond with 2 hydrogens, and 180 degree is the maximum distance that can be maintained by these bonds, because according to VACPR theory it is repulsion which give the shape to the molecule. So the bonds adjust themselves in such direction so that they can maintain the maximum distance and minimum repulsion. So here the maximum distance that can be maintained by two bond is at 180 degree. So this one gives a linear shape. Then here in case of CO2, I draw this shape because I just want to clear that these lone pairs does not give any effect on the shape, because these are lone pairs of surrounding atom. So only lone pair of central atom can disturb the shape of the regular geometry of the molecule. Also, pi bonds does not give any effect on the shape, because these are always with the sigma bonds. So in this case the carbon is having no lone pair and it is having two bond pair, because we will count only the bond pairs of sigma bonds, not of the pi bond. So here the pi bond does not affect the shape. Also the lone pairs which are present on the surrounding atom not give any effect on the shape. Here another example is given of HCN. Here again N is having lone pair, so these lone pairs does not give any effect on the shape, and these two are pi bonds. So these will also not give any effect on the shape. Main factor is this sigma bond and this sigma bond. So here two bond pairs are present. Now you can see here that in this case carbon is less electronegative as compared to the oxygen. So this will taken as a central atom. Here also carbon is less electronegative than nitrogen. So this will take as the central atom. So these are some basic rules. Next we will discuss 3 electron pairs. If there are total 3 electron pairs, in that case the different cases are there. Like maybe out of these 3 electron pairs, all 3 are bond pairs. Maybe one lone pair, two bond pair is present, and at least two bond pairs should be present to form a shape. Clear? So here you can see that in this case all three are bond pairs, and whenever all three pairs are bond pairs it will give a regular geometry, and when lone pairs are present the regular geometry changes and it gives a irregular geometry. So here it give a geometry like this is having a trigonal planar structure, and here you can see this trigonal planar structure with a bond angle of 120. When two bond pairs and one lone pair is present, in that case what happened, any one of these three will remove and it is replaced with a lone pair, as you can see in this case. So it will give a bent structure, and this bent structure is having bond angle which is less than 120, because normally it is 120 as a lone pair is present, and you know that the repulsion between the lone pair and bond pair is more as compared to the bond pair. So this lone pair repel these two bonds, due to which these two bonds come closer and the bond angle will be less than 120 degree. In case of 4 electron pairs, the bond pairs, if bond pairs are 4, in that case it will give a regular tetrahedral geometry, and these are the examples of regular tetrahedral geometries. In second case of 4 electron pairs, 3 bond pairs and 1 lone pair may be there. So in this case, any one of these 4 bonds will remove and it will replace by a lone pair. In that case, the bond angle is decreased from the regular geometry, and the reason is same, that this lone pair and bond pair repulsion is more, so obviously the angle between these three will decrease from 109 to some extent. Okay, so this is the trigonal pyramidal geometry. Next, if there are 2 bond pairs and 2 lone pairs, in that case it will give a bent shape, and in that case the bond angle decrease from 190 and the extent of decrease is more than this previous case in which only one lone pair is present, because here as 2 lone pairs are present and they will repel with more extent as compared to the single lone pair. These are the examples of bent shape. Also, if you observe that in this case a bent shape is there, and in previous case of 3 electron pairs also a bent shape was there. But in that case what happened? One lone pair and 2 bond pair gives a bond angle which is slightly lower than 120. But here it is slightly lower than 109.5, and the main difference is that this geometry is originated from the tetrahedral geometry and that bent shape is originated from a trigonal planar geometry. So it depends upon the original shape, original geometry from which it is originated, or this is the irregular of this tetrahedral geometry. Then if there are 5 electron pairs, in that case, if all 5 electron pairs are bond pair, in that case a trigonal bipyramidal regular geometry is formed and the bond angles are 90 degree, 120 degree and 180 degree. There are different types because these 3 are in one plane and these 2 are in other planes, one above the plane and one below the plane. Clear? So here if one bond pair replaced with the lone pair, what happened in that case? One bond pair will removed. In that case it will form a seesaw structure and the bond angle will be 90, 120 and 180 again. Other cases of 5 electron pairs, if there are total 3 bond pairs and 2 lone pairs, in that case only these 3 remaining, because mostly if the lone pairs are removed, what happened? They will be removed from above the plane and below the plane. Mostly it happens from the same plane because it will give more stable structure. Here you can see that 2 lone pairs are present and the bond angle is 90 and 180. It does not affect on the bond pair because on the bond angle because the electron pair, the lone pairs are present in different plane. So obviously there will be no much difference on the, it is just like a T-shaped structure you can see here. So if as these 3 are present in different planes, so the bond angle will not much affected by these lone pairs. Again, if there are 3 lone pairs and 2 bond pairs, in that case it is having a linear shape. Although it is written here seesaw, it is wrong. It is of linear shape and this linear shape is due to the presence of these 3 lone pairs, and also as these 3 lone pairs are present in different planes, and this is the angle which can be maintained maximum if 2 bond pairs are there. So this one is linear shape, and these are the examples of the 5 electron pairs in which 2 bond pairs and 3 lone pairs are present. Then 6 electron pairs. In case of 6 electron pair system, if all electron pairs are bond pairs, in that case the regular geometry will form, and that will be the octahedral shape. Here you can see that these 4 are in one plane, just like square planar, and this one is above the plane and this one is the below the plane. After that, here you can see that one is lone pair and other are bond pairs, and this one is a square pyramidal shape because it forms a pyramid. These are the examples of square pyramidal shape. This is GIF of the different shape. This one is octahedral, in which you can see that two bond pairs are in different plane and 4 bond pairs are in same plane. Here one is in different plane and 4 are in different plane. In this case also, as the lone pair is present in different plane, so it will not affect the bond angle. Then again, in case of 6 electron pairs, another one is with 4 bond pairs and 2 lone pairs. In that case, it will form a square planar and 2 lone pairs are present above the plane and below the plane, and that will not affect the bond angle. These two are another cases, but these two are hypothetical cases because you will not find the examples of these two cases. Like if the 3 bond pair replaced with the 3 lone pair and 4 bond pairs replaced with the 4 lone pair, because here if you count the total number of electron, then the central atom is having 6 electrons as lone pair and 3 for bond pair. So total will be 9. That is not possible because maximum occupancy in valence shell is 8. So this is only the hypothetical structure. This one is also a hypothetical structure, and it shows that what happened if the number of lone pair increases. Clear? Then these are some limitations of VACPR theory. The first limitation is that VACPR theory was failed to explain the isoelectronic species, the structure of isoelectronic species. Because if two species are isoelectronic, so the structure should be same. But if you take example of IF7 and TEF7 minus, then both are having 56 valence electrons. But this TEF7 minus is not having a pentagonal bipyramidal shape. So for some isoelectronic species, it is failed to explain the change in the structure. Another limitation that this theory fails to predict the structure of halides of group 2 element, which have a linear structure, whereas the actual structure is bent. According to theory, it should be linear, but actually it is not linear, it is bent. And this theory also fails to explain the shape of certain complexes. Mostly the D8 configuration are often square planar and not tetrahedral, because if there are 4 bond pairs, so it should be tetrahedral. But all the metal complexes which are formed by the D8 configuration, they show a square planar structure. So these are the main limitations of the VACPR theory. This is all for today. I hope you enjoyed the lecture. In next class, we will discuss some examples of structures which was explained by the VACPR theory. Thank you again.